Hello again. This video is for Learning Intention 28 and this is part 3 and this time we're looking at independent events. Independent events, and depending on who you talk to, independent might be spelt with an A there. I do all the E's, not important. Independent events, and this is part 3 of Learning Intention 28. Independent events. It's very easy to get these confused with mutually exclusive events. So be careful. Independent events are a different thing. It's where an event isn't affected by other events. So I might say, I'm just going to do some drawing here. So let's say someone flips a coin. Please don't write this down. Let's say someone flips a coin. So here's this person here, they flip a coin. And what's the probability it's going to land on heads? Well, you know it's a half. Alright, let's say that person's flipping a coin and this person over here is leaving the house and they've checked the weather forecast and they want to know whether to bring an umbrella or not. So they've got their umbrella, they're not sure whether they need to bring it, and they want to know what the chance of rain is. So they look at the weather forecast. Probability of rain today is 80%. It's 4/5, say. So it's likely it's going to rain. Checks the weather forecast, brings the umbrella. These two events are independent of each other because flipping a coin doesn't affect whether it's going to rain or not, and whether it's going to rain or not doesn't affect flipping a coin. So if I ask the question, what's the probability of heads given that it's going to rain? So I know it's going to rain, let's say for certain. What's the probability of getting a heads? It's a half. Who cares that it's going to rain? You're flipping a coin. It's independent of whether it's going to rain. And you can use the same argument for what's the probability it's going to rain given that you get a tails. They're independent events. So what does this rambling mean? It means a formula, but I want to do a few examples first. So I've got this picture here. I want to ask the question, what is the probability of rolling a die and getting a 6 and then getting, so you roll again and then you get an odd number and then you roll again and then you get a prime number. So what's the probability of this happening? What's the probability? You roll your die, you get a 6, you roll it again, you get an odd number, you roll it again, you get a prime number. Looks like a tricky question. It's not so bad. So the way to handle it is to say, well, the probability of, let's call it a sequence, the probability of this sequence equals, well, you look at the first one. What's the probability of rolling a die and getting a 6? Well, that's 1 out of 6. Now, the next roll isn't affected by the previous roll. It doesn't matter what you got before. The next roll isn't affected by what the die did before. Doesn't matter what happened before. What's the probability of then getting an odd number? Well, the odd numbers are 1, 3, and 5. So that's 3 out of 6. When they're independent events, you multiply them. That's the key thing you need to take away. And then the probability of getting a prime number, well, what are the prime numbers? 1 isn't prime, 2's prime, 3's prime, 5's prime. So that's 3 out of 6 as well. So that's a sixth times a quarter, which is 1 on 24. That's the probability of rolling a die and getting a 6, and then getting an odd number, and then getting a prime number. The probability of that happening is 1 out of 24. Now, it's really common to think that if, say, I had a coin, and I'm flipping this coin, and I get a heads, and I get a heads, then I get a heads, then I get another 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 heads. It's really common to think that there's a higher probability that the next flip is going to be a tails, because you've got a bunch of heads. The probability of it being a tails here is a half. It's not affected by the previous flips. Thinking that you're more likely to get a tails is called the gambler's fallacy. So if you're wondering about this, Google the gambler's fallacy. And misunderstanding how this works is the reason casinos existed. If everyone truly understood probability, casinos wouldn't exist. So the only reason casinos make a lot of money is because people don't understand how this maths works. Let's have a look at another example. What's the probability of rolling a 6 and flipping a tails? Flipping tails. What's the probability of that? Well, just like before with the example with the rain and flipping the coin, these two events don't affect each other. So they're independent, and we can multiply the probabilities. The probability of rolling a 6 is 1 out of 6. The probability of flipping a tails is a half. So the probability of rolling a 6 and flipping a tails is 1 on 12. Another way to look at it, if you want to confirm that that's true, is to draw this sample space. So what's every possibility that can happen here? So let's have a look at that. Let's do a two-way table so you can get heads, tails, 1, 2, 3, 4, 5, 6. Heads in a 1, heads in a 2, heads in a 3, heads in a 4, heads in a 5, heads in a 6, tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. Well, the probability of rolling a 6 and flipping tails is 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's another way of confirming the answer. Okay, what's the formula we need to know here? The formula is the probability of A and B equals the probability of A times the probability of B given A and B are independent. They must be independent for this formula to work. One can't influence the other. They just have to have their own probabilities regardless of what the other thing is doing. So the probability of A intersection B equals the probability of A times the probability of B given these two events are independent. And if you have been, thank you for watching.